vertical wall is what? There is no flow across this wall, right? Across this wall direction is the x direction. X direction is a partial v partial x, right? So this u velocity, okay, on here and here should be equal to 0. That's our boundary condition for this. So we have this, okay. So we try to solve this equation. Okay, this is a double equation. This is our 3 boundary condition for this physical problem. Okay, and what do you guess? What kind of wave will appear inside this? Can you guess? Is it a traveling wave or standing wave? We just know 2 kinds of wave, right? We just learn traveling wave and standing wave flow, right? One is a traveling wave on the top, one is a standing wave on the top. Okay. For this kind of flow field, this is a physical problem. Okay, so it's a rectangular container, and then we try to generate a wave. Is any kind of wave can be satisfy all these boundary conditions here. Okay. Let's take a vote. Okay. If you think a traveling wave can appear here, please raise your hand. 如果你认为行进波可以在这上面的，你就可以举手这样啊。Okay. One. Just. If the standing wave, only standing wave can sustain or can survive inside this. Okay, raise your hand. Okay. And why? 为什么？为什么只有 standing wave 可以 survive？ 为什么 ？Is any intuition？ 那是直觉。你们有什么直觉？刚刚举手的同学，有没有什么 common 或者什么直觉？你认为 standing wave 才会产生在这个 tank 里面，或者是 traveling wave 为什么？猜的。
想象它是一个很大的一个游泳池，游泳上去，那个会出来 traveling wave 吗
？Okay. Yeah, I just observed. Okay, I can shaking this tank, and then what kind of wave eventually will be appear. You're talking about if you shake the wave, right? If you throw a stone inside here, okay. 如果说我把它okay, I just throw a stone inside here to disturb the flow, right? And try to generate a wave. We can say this is a wave maker, right? 我们造波。Once I make a wave inside this tank, they will start to set up to satisfy all these boundary conditions. Right? And then eventually, what kind of wave will be survive? Okay, 最后会存在什么样的波的形式在这个 tank 里面？这是我的问题。What kind of wave will be eventually, okay, ended? Okay, this wave will be sustained and then continue to vibrate inside this wave, inside this tank here. Okay, some students say traveling wave, some students say standing wave, and any comment from the standing wave student? 有没有任何建议还是猜的 ？Just guess. Okay.
其实两个都会发生。
Yeah. Could be. I say both waves can be happen. Okay, that's another possibility. Okay. Okay, let's go back to what you have read. Okay. Traveling wave, what happened? Traveling wave, this is our what? Traveling wave particle path, right? Inside the traveling wave, we have particle path, either this or this, right? This is all true. And for standing wave, we have a particle path, what? Look like what? Look like this, okay, or this, right? Depend on your location. For the wave inside this rectangular tank, if you consider here, whatever, if you have a particle path here, particle is in this location. The particle is what? Is moving in a circle or the elliptic, whatever. The flow will be penetrating into the wall, right? So here again, okay, particle in this occasion, if you are traveling wave, you will travel like this, the particle path like this. Okay, and this particle path will be violate boundary condition. Okay, boundary condition will not. So only one possibility. What happened? The particle path here should be what? Horizontally or what? Vertically, right? So the particle path here should be satisfied. In order to satisfy this boundary condition, it should be moved vertical. And what's the vertically? That's in the when any wave can generate vertical particle paths, only standing wave. Okay. So when you have any disturbance into this rectangular tank or rectangular vessel, the only wave you can satisfy all these boundary conditions is only the standing wave. Okay. If you don't understand, if you don't believe, I can show you the picture. Okay. This is a fish tank. Okay. This is fish tank, right? As you can see, when you have an earthquake, as you can see here, okay, it's a standing wave, okay, and this is once you shake it, okay, and then eventually here is our anti-node, right? This is anti-node, back and forth, up and forward, okay. So that can only this kind of wave can sustain, can be survived, okay. So based on this physics, okay, you can guess what kind of solution look like inside this. Okay, it's standing wave solution. Okay, at beginning is a traveling wave, no, but once they try to set up, then they will eventually become standing wave. Eventually. But they're back and forth, right? They are traveling back and forth. Eventually, all the unsafe boundary condition will be cancelled and then it becomes standing wave. Okay. So only standing wave can be sustained or can be survived. I say 它可以所有存活的就是 standing wave 可以存活在里面。Okay. The rest of traveling wave will cause this boundary condition. Okay. So anyway, so let's to try to construct this, the wave flow inside this rectangular container, and then so we will try to do is we just eliminate the possibility of traveling wave, right? 我们刚刚把这个波在这个里面，在这个 tank 里面所能够形成的行进波的可能性也把它剔除掉了。Okay, only standing wave. Okay, so eliminate the possibility of traveling wave because of this boundary condition. Because standing wave type, is a possible solution which we can guess. Okay, and what's a standing wave solution? This is our standing wave complex potential. If you from a standing wave, you can see here. Okay, and as you can see here, we have a sign with a z plus IH, and then sine with a 2 pi ct over lambda. So here sine, with a time domain, right? This is time, t is a time domain. So this is time domain will be sine function, or cosine function. So we can written in a more general form. In the time domain here, we have a sine. In the time domain here, we have a sine function like here, and in here, as you can see here, since in the sine 2 pi lambda over z plus IH, z plus I, since z is a complex variable, is equal to x plus IY, right? So that will be superimposed by what? Can be superimposed by sine, cosine, and hypersine, hypercosine. Okay? So for this term here, I can guess, this is a complex potential for standing wave. So the solution for the complex potential or the velocity potential for this physical problem okay, the solution will look like a standing wave. And look like standing wave, I can have a more general form like this. This is a more general form. So my velocity potential can be written as A1 sine 2 pi x over lambda plus A2 cosine 2 pi x over lambda. Multiply, this is another constant, B1 hypersine 2 pi y over lambda plus hyper cosine 2 pi y over lambda. Okay, and the reason is what? Similar here, right? Similar here. We have a sine, okay, sine for this term here, because we will try to guess our solution from the standing wave, right? And this is x plus I, y plus h, right? This is look like, and this is sine, and I multiply this inside makes it easier. It's 2 pi x plus 2 pi over lambda as this, and this I is here. Okay, so I have alpha plus beta, right? Sine alpha plus sine beta is equal to what? Alpha plus beta become sine cosine, right? Sine alpha cosine beta plus sine beta. Okay? So we have this is our alpha, this is our beta. Okay, and multiply. Okay. We have a sine cosine, okay? We can sine alpha, okay, alpha is this, and then cosine beta, right? Plus sine beta, cosine alpha. Is that right? Okay, this is our alpha, this is our beta. And as you can see, beta is what? Imaginary, right? This is imaginary variable. So beta here, this is beta. So beta, if I written this is the I beta, okay? This becomes I beta, right? This is I beta. So cosine I beta is equal to what? Hypersine. So similar we have, okay, what we had before, okay. We apply solution, this one, not this one, okay. Let's go back here. Any formula here? Okay, this one. And sine I alpha here, we have a sine I beta here. And we change to what? I hypersine. Just repeat the similar, okay. And what I try to do is try to evaluate this term here. If you go back to what I just, okay. So here we have the sine, okay. We have the sine cosine, right? Let me see, sine cosine function, okay. Sine cosine, okay. So we have a sine cosine function with a hypersine hypercosine function. Can be superimposed together. Can be our solution form will be look like this. Okay. So I have more general solution form for this physical problem by written. I can contrast from the standing wave solution and try to more general form the solution for our physical problem. For this physical problem will be look like this. Okay, and we try to evaluate the A1, A2, B1, B2, and try to see this can satisfy our what? Can satisfy our Gaussian equation as well as our boundary condition. Okay, that will be. We'll try to find out all these very constant A1, B1, okay, A2, B2, and try to see any possibility. If a solution form look like this, can satisfy all the boundary conditions we have. Okay, so let's apply what? Apply to the bottom wall boundary condition. Okay, now maybe it's easier to have the start from this maybe. Okay, this when x equal to this, what happened? Okay, we have the boundary condition at this location. Okay. Okay, so this is a solution form we have, right? So let's try, this easier maybe. Okay, this is our bottom wall boundary condition. Y equal to 0, we have this boundary condition. So partial p, partial y, and y is here, right? Y is here, y is here. So partial p, partial y, hypersine become hypercosine. Hypercosine become hypersine. We don't have to change the sign, right? And when y equal to 0, as you can see, hypercosine, once we take a derivative, partial phi, partial y, this become hypercosine. And y equal to 0, this become 1, right? This become 1. So we have b1 here, plus b2 times hypersine when y equal to 0, this term is dropped. Okay, we only have a b1 here. So this b1 should be equal to 0 because all this term here, okay, for any location x, this should be, okay, satisfied because any x, partial v, partial y at y equal to 0 should be equal to 0. That's our boundary condition on the bottom wall. So we can immediately find out this b1 should be equal to 0. Okay, this b1 should be equal to 0. Okay, so once we have a b1 equal to 0, so we don't have to consider this term. We only consider b2. Okay, b2 times a1, we define a new constant called d1. And b2 times a2, we define a new constant called d2. So our constant, only two constants only left is this d1 and d2. Okay, so d1 times sine 2 pi x over lambda is this term. Okay, and then d2 times cosine 2 pi x over lambda is this term. And then both of these terms multiply our hypercosine, this term, right? Because the b2 is not determinate. So 2 pi y over lambda and sine. So this is a velocity potential after we apply the bottom wall boundary condition. Okay. So we try to evaluate the d1 and d2 again. Okay, and then we have still have the two boundary condition. Okay, and one is boundary condition is dynamic boundary condition. Okay, this is dynamic boundary condition we should have. So once you apply the dynamic boundary condition for this velocity potential, we just reduce to d1, d2, these two constants. And by applying into this boundary condition here, this is once you do this, you can get this get this equation here. And this equation again, as you can see, for any x location when y equal to h just on the free interface, right? On the free interface should be equal to what? This equation should be equal to 0. And as you can see here, any x, so x can change any location. Okay, so d1 and d2, okay, these two terms may not be equal to 0. This is depend on time, may not equal to 0. But for this equation only equal to 0, we need that. We need inside this bracket should be equal to 0. Okay， 所以只有在这个括号里面，这个一定要等于0，这个 boundary condition 才会 satisfy. So we can using this, okay, assume this is equal to 0, and you can simplify this become our dispersion relation. 就是最后 ，okay. So from his relation, this equal to 0, you can get this relationship. This relation is just dispersion relation we mentioned before. Okay, from the dynamic boundary condition, always give us a dispersion relation. And what's a dispersion relation mean? Dispersion relation relate to what? The velocity, wave speed, and the wavelength. Okay. These two, okay, when you have the certain wave speed and wavelength, the relation between these two, we call this is dispersion relation. Okay, so this is from the dynamic boundary condition. Okay, we only can get this dispersion relation. Finally, we have the boundary condition on the side wall here, right? On the side wall here, this is the rest of boundary condition we have. Okay. Okay, and this is on the side wall. Okay. So the partial v partial x is x equal to positive negative arrow, okay, should be equal to 0. So when we apply this boundary condition, this is our phi, okay, this is our phi, and apply it into here, and we get this equation, okay. You can check because you take the derivative with x. Where is x? X is here, right? So sine become cosine, right? And cosine becomes sine, okay. And then x is equal to positive negative arrow, so this is positive negative arrow here. Okay, when I apply the x location, okay, then we should have this. Okay, this equation should satisfy on the side wall. Okay, and if you see this boundary condition, as you can see, for any y and any t, right, should be satisfied for this boundary condition. So y is here, t is here, so this cannot be equal to 0. Any y and any t, this can be any number. Okay, so only this equation equal to 0, we definitely have inside this bracket here should be equal to 0. Okay, so we end up with have this relationship, right? This equal to this, we have this. Okay, we have this. So we try to find out D1 and D2 have a relationship like this. Okay, these two constants have a relationship like this. Okay, I think I passed 5 minutes already, so we'll take 5 minutes break, okay? And then we can finish this. Okay, this physical problem. Since we're almost done, okay, we apply all the boundary conditions to find a solution.